So next, delighted to announce, to introduce Valentin Plugaru from Chief Technology Officer of LuxProvide. And so on. Okay.
So I will be talking a bit today about what we are doing in Luxembourg in terms of supercomputing, in terms of providing supercomputing to a wide variety of audiences, and to simplify the life for life scientists and to bring data security into the loop too. So we have been created in Luxembourg as the first national platform, national supercomputing platform, and we have been given the mission to democratize the use of these kind of facilities to both the scientific world and to the public sector world and to the private sector world, and to try to bring industry on board in these kind of facilities and enhancing innovation. And the idea is to bring real solutions to life, not only focusing on pure fundamental research, but to bring real solutions faster to market. The mission of LuxProvide was to implement a MeluXina supercomputer, and MeluXina supercomputer is one of the European new generation machines, part of the Euro HPC network of systems, and the first generation that is now operational for some time. And the idea with LuxProvide is to tackle global challenges and challenges that are important Europe-wide and in Luxembourg too, and to bring solutions for decision makers, and to focus on providing intelligent solutions on top of the compute and data platform. So we don't store data just to store data. We want to bring to do something real with that data, so to provide computing services on top and to build this into solutions for our users. We are tackling some segments of activity that are really priority for Luxembourg as a country, in particular space, industry, manufacturing, health tech, and this really means all the spectrum of health related technologies for life science, bioinformatics, personalized medicine, precision medicine, and so on, and also financial technologies, which Luxembourg is quite well known for. Supercomputers have been used very successfully for a long time in all of these fields, and maybe just to focus on two parts. We're seeing a true resurgence in the use of supercomputers, simulation capabilities, but coupled with data capabilities, data analytics, prediction, deep learning, machine learning, AI. And this sometimes is joined in a very nice couple of words, which is digital twins. And digital twins, in particular in the health tech sector for personalized medicine, is becoming a real big thing, because it allows you to predict how, for example, from a cell, how a cell will respond to stimuli, to build this up towards a full human body response models. Of course, we're not there yet, so there have been very good simulations, for example, of the human heart and specialized organs and cells, but not yet at the full body level. But the world is going into this direction by building infrastructures that could support those kind of use cases, and also by bringing software to life that are going to be able to take advantage of the infrastructures to make this a reality. What we have been doing in the past 1 year and a half, well, more than 1 year and a half, but especially in the 1 year and a half that MeluXina has been in production use, we have really focused on democratization activities, so trying to bring people to understand what supercomputing is, how supercomputing can be used in their workflow. And we have been running a pilot program that was quite successful. It brought really a lot of actors from both public sector, public research, and also the industry to start to use MeluXina as a supercomputer with multiple facets, to get a feeling for what they could do and what they could do better, or what they could do more than what they are already doing. And in particular, we, as LuxProvide, are part of the National Competence Center in high-performance computing, data analytics, and AI, part of the EuroCC initiative. And there we are providing a lot of, you will find webinars from our HPC Thursdays initiative that is piloted in the country, which show various aspects for a variety of fields and how people can take advantage of this kind of systems. And we are very active with startups too, and trying to bring promising startups to do something that they maybe have not imagined, by knowing a bit what HPC is about and how to use it properly. To give you a very rapid feedback for what we have seen in the pilots in the life sciences direction. So two highlighted projects that I would like to talk to you about have been in very different ways extremely exciting. So they ran now more than a year ago, but One was actually very interdisciplinary work, and it was work combining traditional simulations with ab initio simulation, first principle simulation codes, but coupling this with machine learning to be able to create databases of properties for molecules and to see how this could translate into something that allows you to build a pharmaceutical application with pharmaceutical applications or new drugs, but to generate things that do what you want them to do, desired characteristics prediction. This is something that was groundbreaking work. Now generative AI is on everybody's lips, and I can talk a bit later. We are really seeing a lot of value being brought by this kind of interdisciplinary work that was really not possible many years ago. But facilities are now there, skills are now there, and models are now there that are really opening up new avenues for researchers, for scientists, and bringing this into the life science domain very deeply too. The other project that was quite interesting was the GigaSum project. So why it was interesting for me in particular was that there were novel uses of new programming language that are enabling scientists to take better advantage of supercomputers. And if I turn back the wheel of time to 10 years ago, many life sciences programs were Perl at the time. They were MATLAB. They were also R. And then over 5 years, well, 5 years later, maybe 5 years ago or so, many of them were ported to Python, and the codes in the Python ecosystem exploded. And now we're seeing this with Julia. So this is kind of a very interesting use of supercomputer facilities, and the community is really in the driving seat. So people say, okay, supercomputers, I don't want to care of a workload manager. I just want to run my code. How can I do that? And the new programming languages that are being developed and the modules that are sitting behind are really enabling this push into the ecosystem of using the systems in a novel way. And it's quite transformative. So in some cases for this particular application, there were some limits into the current models and the software that existed. So they were able to do quite fast only 10 million cell clustering, but with a bit of rework of that code in Julia, they are able to do 10 billion and fast. And this brings up a new kind of possibility into the ecosystem. So very different applications that we're seeing these days, and very exciting from multiple aspects. To give you a bit of a hint of what MeluXina is and what MeluXina looks like, so actually this is the front end of the system, the liquid-cooled components, that is the heavy-duty compute part, and it has a nice picture of a mermaid, of the MeluXina mermaid, which is part of a foundational myth in Luxembourg. So MeluXina being a water-cooled supercomputer, there's a binding with a mermaid, which is a water creature, but that's enough about the mermaid. But the supercomputer in itself was really built as a modular system for taking in multiple type of use cases. So it has a lot of capabilities for running a very fast high-end code, so pure CPU. Also very high-end capabilities for accelerated computing with GPU AI accelerators. And it also sits on top of very capable storage platform with multiple data tiers that I will show you in a second. And this is all together glued with a high-speed fabric, HPC fabric, InfiniBand in this case. There's a lot of software tools that we put on top of it. And there's also a cloud platform that I will really have a dedicated slide for you in a second. So in terms of raw compute power, and this is a very funny thing about numbers, that you can present a supercomputer in very many lights. If you talk about the pure scientific computing, double precision format, ab initio simulations running very deep partial differential equations very fast, the machine is capable in aggregate of 18 petaflops. But if we talk about AI and machine learning, deep learning that can be done, the machine is actually 500 petaflops AI system. So very capable system in terms of computing. We wanted, when the machine was built, we wanted it not to be a machine that is just fast on compute, but it's also fast on data. So the data platforms behind were sized to be to provide per compute node a very high-end capability of data in and out. So the main data platforms both for accelerated analytics and for capacity storage, are sitting beyond the 500 gigabyte per second in throughput, and 190 well, it's actually for read operations, it's more like 220. So extremely capable data platforms sitting behind the compute part. And the play between the two is really key, because also if you look back 5 years no, but 10 years, systems were designed very differently. HPC systems were very heavy on compute and very light on storage. In Luxembourg, the life sciences community is extremely vibrant. So there's the Luxembourg Institute of Health, there's the Luxembourg Center for Systems Biomedicine, which is focusing on Alzheimer's and Parkinson diseases as flagship lighthouse projects. And their needs were always very heavy on data. So the first national platform, when it was built, MeluXina, was also brought up with high-end data capabilities to be able to provide well, the kind of to enable the kind of use cases that we knew would be coming. So the machine itself is actually hosted in a tier 4 data center, so very highly capable. And on the security aspect, the data center itself is an ISO 27001 certified data center for the information security management system. And this is actually a mission that was given to the data center operator, but also to LuxProvide. And on that, I do have a slide a bit later too. So if you look at this picture, this actually shows the components of the machine, and it's quite an accurate representation of what you will find when you will visit us. I don't say if you visit us, but when you will visit us. So in fact, the front end of the machine that you see here is the heavy duty compute part, the non-accelerated cluster module, and the accelerated GPU accelerated accelerator module. And this is highly tightly coupled with the other platform, other part of the platform, which contains a system module for orchestrating workloads with login nodes, with data tools, a cloud platform, specialized compute, and also the DDN storage platform that is having the multiple data tiers inside. All of this is coupled to the European networks, to the giant research network, and to public internet network with redundant links. And all of it as a package provides a lot of capability for running various workloads. The idea being from the ground up to enable the ecosystem to find a bit of, or to find the kind of platform behind that they could use, maybe not as an end-to-end, but at least for part of their pipelines and processing pipelines. The machine on the platform, the infrastructure is extremely complex and very difficult to install and deploy. But then when the user comes, they want to find something that they can use it with. So what we put in place, in fact, is quite a rich ecosystem of tools. The software stack that comprises applications from libraries to real applications, and we deploy this on a recurrent basis, enabling users to find, well, if they want TensorFlow, if they want PyTorch for deep learning, machine learning, or if they want GROMACS or Plumbed. These kind of tools are available day one for them, so that they can just bring their data and start computing. Doing this enables both developers, scientists, and engineers to have a quick ramp up into the system, but of course, people can bring their own tools and use them in very many combinations by doing their own tools and coupling them with the tools that have been built for the machine and optimized. And if I take a look at GROMACS, which is really well known into the life science community, and is typically coupled with Plumbed. So I think from the European, from across the European projects that we're seeing on the machine, I think 7 out of 8 are using GROMACS and Plumbed together. Deploying the tool in itself is quite complex, so we want to take this burden away from scientists and researchers and enable them to just bring data and start computing. And what we are doing with our teams is helping them run this efficiently in a supercomputer environment. And all supercomputers are, well, on our side are beautiful, but all supercomputers are really tailored to some use cases, except if they're really driven to a specific application. So when you have a general platform that is having multiple type of research happening and industrial access and applications running too, you need to find your way, and our teams are helping users understand how to run efficiently on this platform and effectively too, such that they do get the result that they want and that this is as efficient as possible. And we do this from the point of view of the software, so bringing there's the software there for them to already use, but also guiding them in the use in the proper use of these tools, such that the process pinning and so on can really make a huge difference how fast an application goes. So if you're not accustomed to HPC, this requires some specialized knowledge, and that's where we play into the ecosystem. In terms of tooling, so I said that there are multiple. I see the slide is a bit mixed, but the kind of packages that we put in place are actually across multiple type of pillars. So there's a pillar on compilers, languages, and programming languages and performance tools that enable developers to bring applications to life, new applications to life. But we are adding a lot of value-added components on the system too. So this goes from libraries and the tools that allow you to parallelize code, to run code efficiently on accelerated compute GPU AI accelerators, numerical and data libraries that allow you to use various data formats, visualize them, and so on, to frameworks that allow you to bring models, to run models, and to develop, and then real applications that are where you just bring your data and you start using it. We are doing we are putting on the machine also some quantum simulators. For now, we are just exploring what the people would be using this for, but the machine was planned indeed to be able to provide a wide variety of tools for everybody to be able to find their way inside. And I said that Julia is quite interesting for life sciences community, and we are seeing that that the use will explode. In fact, if 5 years ago Julia was at ultra early stage, today the community is actually building for the life sciences community is building a lot of libraries and packages and modules and integration with other tools that is really tremendous. In fact, it goes from I think I saw the TSNE mentioned in a prior slides from one of the other speakers, and there's kind of libraries and models that are now being brought to Julia as an easy ramp up for scientists to do their work without understanding too much about the complexity behind. And this is really transforming the ecosystem and what scientists can do. And there's a very recent nice article from Nature which is actually exploring this to a high degree. And that's I really recommend to take a look. It's really very, very interesting. Placing a well-optimized software stack is well and good, and many HPC centers do that. We are also allowing people and enabling people to use containers, and containers for life sciences have been really big for quite some time, especially from the point of view of reproducibility. So reproducibility is really key in life sciences. Our bioinformaticians a long time ago were requesting this, and at the time on HPC it was not really possible to use the technology that existed at the time. So Docker containers were not safe to use in an HPC environment. But then Singularity, Shifter, and other kind of tools appeared, and it became magically possible to run containers and Docker containers on HPC. And this really brought a resurgence in how people are able to use supercomputing platforms for data analytics workloads linked to life sciences. So we are having a Singularity C. There's multiple variants today of Singularity. Obtainer is another variant, but the idea is that with this kind of tooling in place, you can run encrypted containers, so you can be sure that your workload is secure, but you can also do accelerated computing natively, so you can take advantage of the underlying platform in your code, and building together all the huge set of libraries that you need to do your work, and the huge pipelines. So bioinformatics pipelines typically comprise not one, not two, but hundreds of applications in some cases, and this is tremendous effort for people to do. And typically you have one engineer that knows how to build this together, but then this is reshared into the community of users that are working on a project. And containers are typically the way this is happening, and we are enabling them to do this on MeluXina too. So a typical use of a supercomputer, if I may make a small introduction to this, has been to go through SSH, secure shell, transfer data through SFTP to a login node. The login node is connected to your data storage tiers, the parallel file systems, GPFS, Lustre, others. And then run your computation through Slurm Workload Manager. And life sciences people have typically had quite a lot of problems with this, because this is not working the way they were working. So rather than will make everybody change their mind into how they work. We are trying to support an evolution of this kind of use cases to bring layers of tools in place that are allowing people to do what they want to do without changing drastically the way they're doing it. So as a small break in this, what we've seen in the past, and I'm bringing this into the AI domain. By the way, this picture is kind of wrong. Today, seeing how generative AI is working, I think this should be really shifted. I mean, it was meant from Gardner to that we are somewhere here, and in fact, I think we are still on the upscale of what the ecosystem can do. So please disregard this image quite deeply. But what I wanted to highlight here is that AI is going through a maturity phase too. And in the past, this actually mirrored for me a lot of what our bioinformatician and life sciences people were saying. They were saying, we want to run a pipeline. We don't have just need for simulation. Our workload is actually data analytics, is data driven. We have a 1 terabyte FASTA file, a pure text file. Our code is not scalable. You need to run this. We want something that is also interactive. So how do you do that with a supercomputer? It's quite hard. And in the machine learning world, people were having the same kind of problems. They tried to run some deep computational workload, but sometimes the effort was quite manual. So you had, for the machine learning setup of the code, sometimes they were doing it with a JupyterLab notebook, but running it in the first command and the third one and the second one. So this was also not reproducible. So the machine learning world, the AI world, was having the same kind of problems at the time as the life science world. And what is happening in the machine learning world, there's this new word on machine learning operations, which is actually has a need for the pure computation side, but also for model serving, for analysis, for fine-tuning. And this requires much more than just compute capability. It requires some cloud-like capability. So today, cloud supercomputers are a thing, or there's huge cloudification efforts behind supercomputers. And this is where we are quite active these days too, to try to bring to MeluXina a more cloud native part on the on-premise cloud platform that we have, that will be a gateway to running these very complex use cases that glue together various stages of an application pipeline. This will enable, of course, MLOps tooling, but for bioinformatics, in particular, I assume that this is going to be quite tremendous too. And this will allow to use applications that are, well, in some case, you want to run a visualization of how a model behaves, and this is very difficult to do in a pure batch environment. But this could be coupled with a batch pure compute-oriented environment, and the glue of the two will bring new opportunities into the domain. What we are doing in terms of security and data security is quite well. I can explain it in one slide. We have been given a mission to be set as a trusted and secure center. So our effort in the past years was to go for an ISO 27001 certification for information security management, and this has been achieved at the end of last year. And this means that there are policies in place of how we're doing our activities, the patch management, how things are done from an operational point of view with monitoring. And in fact, the more practical things for you, and if there are system engineers in the room, I'm not sure, but it means that we put in place a lot of immediate things that are useful, that are very different than when you go to a large supercomputing center that is seeing not only your specialized workloads, but many workloads coming from many domains. So what we put in place, for example, was anonymization of projects, of usernames, of very simple things that can actually make quite a big difference, but also making the workload manager with all the privacy settings such that different projects do not see each other. There's node level scheduling, so your workload is not running in the same node as workload from another user. And in any case, processes are being encapsulated such that you don't see what somebody else is doing. And there's data on the data at rest encryption on all the storage platform, and there's the security built into the platform at multiple levels, from when you log in to when you run your computational workload. I think I'm running out of time, so I will maybe conclude on this slide. So we're seeing this tremendous generative AI and large language models being very much in the spotlight these days. And it started with large language models, and it's something very practical, and chatbots are a tremendously nice example. But indeed, we're just at the start of a slope, because this is now being applied to many domains, not just to text, but even just being applied to text is quite fantastic, because the foundation models that were spoken about before are something that will be able to be customized and tailored to specific industries and to specific fields, and this will bring new opportunities and new possibilities. And we've been hearing of the NVIDIA NeMo, the BioNeMo tooling in a speech this morning, and those are kind of tools as well. The NeMo is something that we're bringing to MeluXina with help from NVIDIA too, and we see the true potential that this will bring in people taking advantage of a large supercomputer for building specialized applications and very deeply performant solutions that will help guide decisions for tomorrow. For in the pharma industry, this has really tremendous potential. So this has been a very crash course into what we have been doing. I really welcome an opportunity to talk together a bit later after, well, in the panel and after lunch too. And this is MeluXina with the door open. So I opened a bit the door for you to ask a question. So I hope it was informative, and sorry for speaking so fast.
Thank you.
Thank you.
Thank you.